So no other announcements this week, and so I'll just get straight into it. We've got a guest speaker today joining us from the Cognitive Robotics Lab at TU Delft, but I understand he's sort of mid-move from his previous role. So Cosimo Della Santina received his PhD in robotics from the University of Pisa in 2019. He's been a postdoc at CSAIL at MIT and at the Technical University of Munich in Germany. And from 2020, he's been affiliated with the German Aerospace Center, DLR, as an external research scientist. Cosimo received the Eurobotics George Girault PhD Award in 2020 and the Fabrizio Flacco Young Author Award from the RAS Italian chapter in 2019. He was also the finalist of the European Embedded Control Institute PhD Award. Cosimo's research interests are in modeling for control and model-based control of soft robots, combining machine learning and model-based strategies with applications to soft robotics and soft robotic hands. And today, Cosimo has joined us to deliver a talk entitled A Model-Based View to the Grand Challenge of Building an Artificial Brain for Soft Robots. So I'm very excited to see your talk today, Cosimo. Thank you very much for joining us. Please do take it away.
Thank you very much for the introduction, Donald, and thank you very much for having me here today. So let me start. So here we can see few examples of the many that we can easily spot in the animal kingdom of living beings exploiting their body elasticity to perform tasks in an efficient and effective way. And if we have a closer look at what is going on, we could even say that these animals are, these animals are using much more the physical intelligence provided by their body elasticity rather than some high-level computational resources. And this bold statement has been backed up by centuries of research in biology and biomechanics and motor control. For example, there have been a lot of experiments on the cerebrate animals doing presenting intelligence motor behavior. And this is I think one of the very first picture on the right, one of the very first of these experiments, which is the one by Galvani in 1791. And more recently, this has become the topic of interest of philosophy of mind with the extended mind hypothesis. But what does it really mean that elasticity can be the source of physical intelligence? The idea is very simple. If we look at just one muscles, this is of course an actuation element for a living body, but we also have these two elements, which are the tendons that connect it to the bones. And if you stress these elements, for example, imposing a certain length, what you discover is that their behavior is very much close to the one of a linear spring. So you can really think of a joint of a vertebrate animal like something like this, or something that has rigid to rigid links presenting the skeleton, a joint, an actuation mechanism, and a spring that can be seen either in series to these elements, but when this element self-locks, becomes in parallel to this joint. And it's not the scope of this talk to go into detail in this aspect, but just to motivate you that you can easily show that even a so simple system can endow the animal with the unmatched ability of interacting in a structured environment in terms of safety and in terms of robustness. And I think even more interesting, it can allow dynamic motions by serving as a energy tank. So animal can really put the kinetic energy while performing dynamic task into this elastic element, and then release it again to obtain all the kind of nice behavior that we observe in a real animal. So there is no wonder that the robotics community started to think, why not introducing some elasticity in our robots? And this produced so-called soft robotics field. This is a definition that we are giving in the Encyclopedia of Robotics, which is soft robots are robotic system embedding in their mechanical structure purposefully designed compliant elements. So according to this definition, we have two classes of subclasses of soft robots. We have the one more inspired by the invertebrate part of the animal kingdom that we will call Continuum Soft Robots, and the ones more inspired by the vertebrate part of the animal kingdom that we call articulated soft robots. So in the latter, we have, as I said before, a rigid skeleton and then all this kind of elasticity and softness coming from other elements. While in Continuum Soft Robots, and they would be the very core of this talk, we have the elasticity which is distributed along the wall structure, like an octopus or an elephant trunk. And you can Google soft robots, and you can really very well see how many cool soft robots are nowadays around, built using all kind of technologies and all kind of techniques. And it is, I think, therefore, consider all the motivation that I started with and all the cool architecture that are around. I think it's therefore quite surprising to discover that rigid robots are still outperforming soft robots in most of the practically meaningful applications. And in order to understand why this is the case, I think it is worth to go back to the animal kingdom and realize that animals behave so well because they have a synergistic interaction between an intelligent body and an intelligent brain. While right now in soft robotics, most of the attention has been devoted to building intelligent bodies, in Continuum Soft Robotic at least, and not enough, in my opinion, work has been done in classic view of intelligence, so in computation and in the, let's call it, in the artificial brain of our soft robots. I think therefore that control, it's really a grand challenge within the soft robotics field. I mean, I mean control in a very broad sense, but the idea of building artificial brains for these soft robots, and that if then solved, at least partially, can enable the application of this technology to a vast range of new fields. And there are a lot of approaches trying to attack this problem. I'm not going to discuss them for the sake of time. I will just present my view, my catch to the problem, which is the model-based one. So on a very high level view, what we have is a soft robot, which is an infinite dimensional system, so a continuum system, a kind of octopus, as I said before. We have a set of sensor readings, a set of actuations that we can use to act on our soft robot and the actual behavior of the robot. And we have a decided behavior that we want to implement by means of model-based feedback control. So this is a super high level, super general framework. And I think it's surprising to think that very few results exist in literature. And actually, when I started to look into it a few years ago, we can say that no results were yet there, at least in the fully dynamical sense that we are used in robotics, and I'm going to introduce you in a second. However, I mean, this is astonishing, I think, but if you think a little more about it and you scratch a little the surface of the problem that we are trying to solve, what we can realize is that the problem is actually very hard, because soft robots, to be modeled exactly, needs continuum mechanics that in turn produce partial differential equations as output, that in turn are quite difficult to be handled directly using classic, I mean, not classic, but advanced tool in control theory. On the other hand, our articulated robots, so both of the rigid and the articulated soft kind, live into the discrete world. So the body can be modeled using standard rigid body dynamics tools, machinery, and what you get as output is this set of ordinary differential equations that we are very much used to, and can be then used to derive model-based controller using all the standard tools that we have in nonlinear control theory. So at this point, one can ask herself or himself, and this is what I asked myself a few years ago: are we helpless at this point? So can we just have to accept that we cannot control soft robot using model-based strategies? Or is this some hope to bring some of the knowledge that we have in the discrete world of the technique that works so well in the discrete world and bring them on the continuum world? And in order to answer to this question, I think it's useful to go back to the very basics. And if you take a beam, which is a planar beam, which is the simplest continuous mechanical elements, and you apply a pure torque at the end of this beam, what you observe is the beam is going to curve with a curvature which is constant in space, but possible variable in time. So under this condition, this infinite dimensional system can effectively be described by just one variable, being the local curvature of the beam. The next step is realizing that many soft robots are made as a sequence of segments with where torques are dominant with respect to forces. So what about describing the behavior of each of these segments has a quasi-constant curvature segment, as you can see on the left, and describe its configuration with just one variable being the average curvature. One can then put everything together, and what you get is a model of the robot's kinematics, which is typically called piecewise constant curvature model. And what this model effectively does is collapsing the configuration space of the robot from an infinite dimensional one to a finite dimensional one, where more specifically the configuration is the collection of the local curvature of each of the segments. However, this is not enough for doing model-based control. This is just a kinematic model. On top of that, we need to add a description of the inertia distribution and a description of the impedance distribution, and then we have to combine all together in a coherent model. What you get is what you see on the right of this slide, and effectively what we are able to do is to describe the dynamics of this planar soft robot as a set of ordinary differential equations in a small number, contrary to like finite element models. And each of the variables has a clear, direct physical meaning on the real system. And most important of all, these equations have the structure that you are very used to in classic robotics. So now that we have a model that we can relate with, what about trying to solve real control problems? And if you are a control guy working in robotics, probably the first challenging problem that is coming to your mind is trajectory tracking in configuration space, that in this context become trajectory tracking curvature space. So we have for each of the segment a desired pattern of curvature, and we want to devise a controller that eventually brings my robot to follow this prescribed pattern in time. This is the block scheme of the algorithm implementing this this behavior. I mean, the algorithm solving this problem, and let me navigate through it very quickly. On the left, we have the desired curvature and its derivatives, and on the right, the actual curvature and its derivatives. And please keep in mind this second ingredient, because it will be important in about 10 minutes, I guess. We have then the first part of the actual controller, which is an impedance-based feed-forward action, compensating for elastic and damping effects. And then we have a feedback compensation of the inertia terms with a PD plus-like structure. And we're able to prove global asymptotic stability of the trajectory, equilibrium trajectory, Q bar, using standard Lyapunov methods. And this is, I think, from a theoretical point of view, pretty nice, but still not enough. We are roboticists and we want to see things work in the real world, in the practice. So we decided to build a real system together with Robert Kachman, Professor Robert Kachman. You can see it while he's deforming this soft robot in the left of the slide. And on the right of the slide, you can instead see the robot. It's made of 6 segments, each of one. I don't know if you can see my mouse, but this is one of the segments. So you have 6 of them. And each of them can be independently actuated. You have 2 chambers in them. You will see them in a minute. And you can inflate separately the 2 chambers in order to create a torque at the two ends of the segments. So we took this system and we started to play with it. Together with our controller, we tried to follow some trajectory. This is just one of them. Is a cosinusoidal evolution of curvature in times for each of the segments. And this is, as far as I know, the first example of a soft robot, a continuum soft robot controlled using model-based feedback control, at least in the fully dynamical sense of the term. And on the top left, you can see the performance in tracking, which I think are pretty good, all consider the technological limitation of the systems. And in the bottom left, you can see the quite nonlinear pattern of actuation that is prescribed by the controller. And just because one evolution is never enough, we tried a lot of different trajectories with different amplitudes and different frequencies. It worked pretty well with all of them. What I think is even more interesting is that we tried to follow other kind of trajectories, maybe more complex ones. And personally, I like a lot the one on the bottom. And I like it because what we are trying to do here is to keep the bottom 2 segments still as if they were rigid, while instead they are, as I showed you before, quite soft, while the top part is oscillating. And in order to do that, the controller needs to have a very good understanding of the dynamic coupling between the top part and the bottom part. Because what is going to feel, these segments are going to feel centrifugal coupling and Coriolis coupling between the top part and the bottom part. And you can clearly see that in looking how the chambers are bulging. You can see they are bulging with a frequency which is twice the frequency of the top part. And this is happening because the torque that they are applying is compensating for centrifugal terms that goes with the square of the velocity of the top part. So if you square the sinus, what you get is something which has double the frequencies. Okay, so as I said, it works pretty well also in this condition, but still, it's I think it's not enough. But it gives us hope that this way of reducing very much a lot the complexity of the problem, but still keeping the fundamentals there, and then using advanced nonlinear control can be a good strategy for controlling the system. So we said, why don't trying to solve different control problems with the same strategies? So what about some Cartesian impedance control too? I'm not going to detail into this. We can maybe discuss later if you are interested. But what we are using its Cartesian impedance control is to go in contact and trace this surface without any knowledge of the contact forces and any knowledge of the environment itself. And then we did a bunch of works to extending this framework to the 3D motions. And we also did some more applicative stuff by building this large-scale soft robot. And here we have that each of the segments here are controlled as if they were one separate custom curvature segment moving in 3-dimensional. And so the controller is compensating for elastic terms and gravitational forces. So I think that this framework is working pretty well, all considered, but I don't want to give you the impression that this solves the problems. Quite the contrary, I think that we are still at the beginning of our climbing our mountain of model-based control of soft robots. There are still a lot to do, both in terms of laying the theoretical ground and in terms of moving forwards toward the real-world application. And I will now give you a brief overlook on what I'm working right now in both the directions. So let's start from the formal, the theoretical ground. Yes?
Really quickly with a question from Teja.
Of course.
Ted is one of our postdocs, and he's asking whether you're using tracking markers to track the current state of the robot. And I think that question came up a few minutes ago. So it would have been for the walking robots, I guess, Teja, is that right?
The one before that with the bending.
The bending robots.
Okay. Can I answer to that question in 10 minutes, because I'm going to go back into that problem with several slides. So
okay, no problem.
I think it's better if we keep 10 minutes about this other stuff, and then I will really discuss in detail that issue.
Good, thanks.
And okay, so let's talk about more theoretical things. I will go very fast on this, but it's just that it's really the part of the things that I'm focusing my attention on. So I just want to give a spot about them. If you want to know more about this specific paper, we publish it as a IRAP plus Arial paper, and so you can go online, and as you know, you can download for free all the videos, and there is a 15 minutes video, if I remember correctly, describing all this stuff in very much detail. But as I said, just to give you the idea in a nutshell, what I'm doing here is to say, okay, let's go back on a segment and let's consider the exact description of this segment. So no approximation to start with, and you can describe the configuration of the system as the curvature function. So the local curvature of the segment at each time step t. So the curvature function is this kappa here, and s is just a geometric value, is the local position along the local configuration, not the configuration, sorry, the local coordinate along the shape, the robot shape. So this is effectively a function for R2 to R. And you can hypothesize this function to be analytical in this local coordinate. I think it's a reasonable assumption to do. And what you get is that you can open this function as an infinite summation of terms having, which are basically, form basically an infinite dimensional polynomial thing. And then this induces a very simple way of approximating this function in, let's say, in the Taylor-like sense by truncating the summation at a certain level. And what I think it's very important here is that M can be as big as we want as soon as it is not infinitive. So I like to call this approach quasi-exact, in the sense that it's not exact because m should go to infinity to be exact, but still all the kind of calculation and reasoning that you want to do, you can do them for a generic m and then be as precise as you want, still being in a finite element, finite word description. Why is that? Because now you clearly see here that the only part that it's evolving in time is this theta. So you can take this set of theta, these weights of this polynomial, as the configuration of your segment. And what is particularly nice of this formulation, I think, is that theta 0 is exactly the constant curvature approximation of the shape of the segment that we used before. So it's really a direct evolution of the constant curvature model. This is the reason why I'm calling it polynomial curvature model. And you can write, as I said, the dynamics of the system. You can clearly separate the constant curvature term for the higher order deformation, and you can do all kind of closed loop control using this model. As I said, if you want to know more, please take a look at the video or write me an email. We can discuss or ask just question now. I mean, I'm happy to discuss it, but for the sake of time, let's go over it. And very quickly, the next step that I'm taking in this direction is to take inspiration by all the literature that we had in the control theory in the 90s about building these low-dimensional template models of underactuated robots, like the Acrobot, the Pendobot, the Furuta Pendulum, and so on and so forth. So they were all two-dimensional systems with one degree of actuation. And a lot of very interesting insight came out of what could and could not be done while controlling underactuated mechanical systems. So my idea is now, that I'm working on now, is to propose similar models for the soft robotic problem as this soft inverted pendulum, which has, again, 2 degrees of freedom and just one actuation, which is this torque that you have here at the tip of the robot, and start thinking about, very in detail, about the control problem. For example, doing some feedback linearization to see what can and cannot be done. Again, I'm not going into the details, but these are the kind of things that we can do, at least in theory. So we have this very soft system, and we can close a loop to stabilize the vertical condition, which is a very unstable one, as you can imagine. And this is just an example. Starting from this green initial condition, the controller is able to bring the robot back in the vertical condition. This is the evolution of the state of the robot. Okay, at this point, we could start saying that we are set to getting a sense of how model-based control of soft robot can be done. And one can even come and ask, okay, but you started with a motivation which was very, very connected to the real world application. So are we now ready for the real world application, or that we have these controllers? And my answer would have to be not really. And in trying to understand why this is the case, I think it's useful to go back to the first robot that I showed you. At least this is what I show you of the robot, but this is what we have. And I think this is answering the previous question, because this is a motion capture system. And you can easily realize by looking at the algorithm that all my algorithm required a stream of high quality, reliable information to work. I thought they are quite robust to model uncertainties, being a very abstract description of the model dynamics. They still need all this information coming with high quality and reliability. And this is something that I think is perfectly fine for in the lab experiments, but not so much if you want to go in the real world, because in the real world, of course, you cannot use motion capture system, and you are completely left blind when you try to do that. So I think that a very important sub-challenge into the problem of building brains for soft robots is the sensing one. And this has a hardware part, which is not really my field, but I will briefly discuss as well, which is building new sensors that can produce proprioceptive information. And then the algorithmic part, which is to build observers that can make sense of these sensors to inform the controller. So this is the other of the robot that I show you, or that I'm using for this work. What we want to do is therefore to add some sensors to the system in such a way that its softness is not corrupted. And this work that I did with Professor Ryan Truby, and while we were both at MIT, and he came up with this very interesting design to build soft skins to measure deformations in soft robots. It's probably better if I just show you a video. The idea is to start from an off-the-shelf material that you can just buy online. It's pretty rigid. I mean, you have some softness, but still it's pretty rigid, and you cannot just pick it and put it on the robot. What you can instead do is to create some kirigami pattern on it to make it soft. And then what you do is just glue it on the real robot, as you can see here. And in the end, what you get is a kind of strain gauge, so a sensor that correlates, which output correlates with the deformation of the robot. That is just a very soft skin that you can put on your robot without doing any modification to the initial structure of the robot itself. Okay, so these are our sensors. We plugged 4 of them on each segment. And with different kirigami pattern. I'm going to show you in a second the kind of very bad behavior that this evolution that this sensors produce as output. They are the output it's the difference of potential between the two ends of the sensor. So as we often do when you don't know how to make sense of your data, we said, why don't using some machine learning, and more specifically some deep learning. But I don't think that this really solves the problem by itself, because it's clear what you want to have as input, but it's not clear at all what you want to have as output, because the shape, you cannot just have the shape of the robot, because the shape of the robot is an infinite dimensional system, an infinite dimensional function, as I said. So quite difficult to have it as an output of your network. The trick that we instead introduce here is to use a new kind of kinematic model that I will not describe in detail, but is one of the extension of the model I discussed before to the 3D world. 3D world also having some elongation component. And this model, kinematic model, is really serving as a model-based extractor of a latent space, a small dimensional latent space for the machine learning algorithm. So what we are doing here is to have as output of our machine learning block, a deep learning block, the description of the robot within this model, which is then mapping this description back to infinite dimensions. And this is, I mean, the model is in the end just some function going from R3 to SE3. And this is, as I said, what happens, you go from infinity, you are able to reason in low dimensional, and then you go back to infinity by the kinematic model. And I think the beauty of this is that in the beginning and in the end, we have both on hardware level and mathematical level, things that can be easily replicated and combined within each other. Well, this meaning that we can just proceed to sensorize the whole robot by just replicating the same structure on all the segments. And as output, we will have a set of SE3 elements that we know very well how to combine between each other. and to obtain in the end the final shape of our soft robot. Okay, however, as we all know, deep learning is a big part of it is data mining, is collecting a good data set. So how we did that? We took our robot and we put it again in the motion capture system. And what we want is, in the end, an algorithm that works as well as the real motion capture, but it works only using the sensors that we developed. So what we did was to create a sequence of random actuations for our robot, and we applied them for several hours. And we collected data from the sensors, and you can see the evolution, the very strange evolutions on the left that I told you before. These are difference of potentials, and these are the expected input to the network. The expected output are again taken from the motion capture system, which produce a set of SC3 elements for a set of finite number of points along the robot structure. And then we devised a very simple algorithm that it's going back from this set of points along the infinite dimensional structure to the finite dimensional description, inverting the kinematic model. And in the end, you have all these pairs of raw potential differences and this low dimensional description of the robot shapes that you can then use to train your network. And these are the results of this training. These are simple motions that were not part of the training set. And you can see in red, the behavior has directly measured by the motion capture system. And in black, the behavior as estimated by the network, by all this structure that I discussed. And again, it's important to stress that this black thing is only relying on this onboard sensor, on this proprioception. And you can see it works pretty well. It kinds of filters the transient as a kind of low pass filtering behavior that we are still trying to understand if it is due to limitations in low pass filtering of the sensors, or it's a low pass filtering imposed by the network. And this is pretty much work in progress, but still I think it's a good result. And this is what happens in more challenging random inflation. Again, these were not part of the initial data set that we used for training. Okay, this was the picture that I started with. This is not really a complete solution, but it's something. We have our sensors that I think are nice. We have not really an observer, it's more something observerish. It's not relying on the full model, just on the kinematic part, but still I think does the job. And then we have as output the configuration of our robot. We have still to close the loop and to show that this actually is enough. It's enough information for doing closed loop control. Although I'm quite confident about it, still we have to try it. However, what we did was to say, what about trying to extract more information from the architecture that we already have? So what about thinking of extracting some external forces? Again, yeah?
Yeah, quick question. Abdallah has a question, and I'm not sure I'm following it, but you probably will. At what point is the delta X and delta Y calculated? Abdallah,
okay, let me go back. He is referring to the let me go more quickly to the thing. So he is referring to the model of this this low dimensional model, kinematic model, and the delta x and delta y are exactly two of these guys here. So it's this kinematic description that we have. I don't think I have a picture, unfortunately, with me, but it basically is a way of connecting all the points along the segment shape with these three variables. And one variable, we call it delta x, and it's how much you are bending in the direction of the local x axis. Delta y is how much you are bending in the direction of the local y axis. And then you have small delta L, which is how much you are elongating along the main axis. And these are the three variables that we use as latent description of the segment shape, and they are the output of this network. And you have the ones for the first segment, the one for the second segment, the ones for the third segment, and so on and so forth.
Abdullah, does that answer the question? Feel free to turn on your microphone. Not hearing you, Abdullah. Maybe let's assume that addressed it. Oh, he will type. He says the slide with the results, please. The slide with motion capture results. Yeah, that looked like maybe it.
This one?
Yeah. So at what point delta x and delta y were calculated on this slide?
I mean, this slide shows the output of the wall architecture. So you have this delta x and delta y, which are the latent space in which the network is working, and you cannot. I mean, we are showing them their evolution as compared as appearing in the validation set, but the output of the network is really this black line, directly all the shape of the robot. And so they are calculated. You cannot see it here because they are calculated in the middle of the derivations, and then they are used to evaluate all the shape through the kinematic model.
Okay, well, I think that's pretty good for now. Abdullah, if you have further queries, can you see if you can get your microphone working, and we'll have more of a discussion at the end of the talk.
Cool.
So thank you for that, Cosimo. Please do continue.
Okay, let's go back here. So I'm actually quite close to the end of the talk. So this is just literally one slide about this other problem, but again, it's your work. It's just been accepted by Arial plus Iris. So very soon more information around about it. But the idea is to think that if you know the model, and this time let's say the full model, partially the full model, not just the kinematic model at least, of the robots, you can know where the robot should be when you apply a certain control input. And you can sense, using the algorithm that I discussed before, where the robot actually is. And so the intuition here is that by comparing where the robot is and where the robot should be, you can regress some information of the interaction forces that are provoking the shift from the expected configuration. And we formalized this idea using a disturbance observer that we augmented again with some machine learning, this time using Gaussian process regressions. So a more Bayesian description of the problem of the machine learning part. And we did that because in this way we could integrate it directly into the machinery of the disturbance observer and prove stability of the observer under uncertainties. Yeah, we did, and these are the kind of experiments that we did. You have the robot going around, and we are poking it with a stick, and we are classifying and detecting and quantifying the kind of interaction that we are undergoing. Okay. So that's it for this presentation. What we did today was to first go into how you can build models and model-based controllers for soft robots that actually work into the practice. Maybe introducing some approximation, but looking at the effectiveness first of the controller. We gave a look on how these ideas can be extended on a more theoretical level to more exact description of the robots, and how we can continue in that direction, although it's pretty much at the beginning. And at the end, we looked at the problem of producing propositive sensing for our soft robot in a way that will allow us to close the loop outside the laboratory. And I hope I was able to convince you about the feasibility of doing all of this using model-based technique, at least partially model-based techniques. And this is probably the most important slide of all the presentation, is acknowledging all the great co-author, co-workers that I had during my research so far. And before ending the presentation, let's just do some self advertisement. We have two open calls about soft robotics. One is a special issue on frontiers on soft robotics, on humanoid robotics and sensor fusion and machine perception, which is about all that concern planning, control, perception, all that it's algorithmic with compliant and soft robotic end effector. And we have also this award associated, which would be 2 papers, 2 fee waivers for the 2 best papers that are accepted. And then we have also a call for posters that will be associated to another special issue for this workshop about application-oriented modeling and control of soft robots. Again, here we have awards, 3 awards that are sponsored by Disney Research. So I hope that some of you would be interested in those calls and submit some nice research to them. And that's it. Thank you very much for your attention.
Okay, wonderful. Thank you, Cosimo, for a wonderful and stimulating talk. That was great. I would like to open the floor to questions. So if anybody has a question for Cosimo, you can raise your hand in the participant panel or type it in the window. And I wonder, to get things kicked off, Abdallah, if you had a follow-up query to what you were asking about earlier. I see you've typed in the window, the 3D figures have plus or minus 100 mil, while Q1, Q2, and time has 0 to 6 millimeter range. Do you want to turn your mute off and ask our speaker a question?
Yes, hi. Is it okay?
Hi, Abdullah.
Yes, hi. Thanks for the presentation. Actually, there is a question for Teja before this one. I just wait in the queue then.
Teja's question came up during the talk, so he was talking about tracking. I think we've addressed that.
Okay. Okay. So if we go to, yeah, this is the slide. I see the 3D figures, they have plus minus 100 millimeter. And if I go to the 2D figures, I can see the range is between 0 and 5 millimeter. So it's like tiny part of the full range above. That
Yeah.
question, so Q1 and Q2, where is it exactly in the full length?
Okay, so this, I'm really sorry that I forgot to put, let me check, double check if I have them by any chance here, but I don't think so. A picture would be quite nice to have of the kinematic description. I don't have it, but okay. The idea is that of this kinematic description is the one that I said you before, but there is a free parameter in this model, which is let me see if it appears maybe here. Yeah. So we have this free parameter, which is this small d here, which appears only here in the forward kinematics. But then if you want to do the backward mapping, which you do here, it appears in a lot of places. You can see here, here, and here. And this effectively, you see that appears at dividing. And it's effectively a scaling factor for your description. This is these are actually the parts in which your low dimensional description is produced. These are the three variables of the low dimensional description, and this free variable is a scaling factor. So if you want these values to be coherent with the more or less the displacement of the real system, you have to take this d as the radius of the cross section of your robot. So if you have the cross section of your robot, you can this one, for example, is a circle, and you can take d as if it was the radius. We did not do that. We just put it there, d equal to 1. The reason is just because it doesn't really matter, because in the end you can prove, and we do that in another paper, you can prove that this is a complete description of the robot's behavior. So it's, in a more mathematical sense, is a complete atlas for the configuration manifold for all the possible d. So it's true, it would be nice to have d scales in such a way that these values are of the same size of the motion, but it doesn't really matter. And since they are in this work just an internal description for our robot, we said just put one there. And this is the reason why you typically would have a very small d, and this would amplify the your values to, if you pick d in this way, you would amplify this 5 up to 100, more or less.
So, so if we put the correct value of d, that means the measurement will be at the tip of the actuator, at the far end, the free end. Is that the location for the real values, delta x and delta y?
No, sorry, can you say again?
If we put the correct value of d, that means the delta x and delta y will be the values at the tip of the, or the free end of the actuator.
No, they would be of the same order of magnitude, but they will not be the same value. What they are is actually it's the semi. For example, delta x is the semi differences between the length of this arc and the length of this other arc. And delta y is the same, but for this other arc that you cannot really see well because it's going in this direction. So it's effectively a measure of how much you are bending one direction of the other, because if you are in straight configuration, the two arcs are just strict lines with the same length. If you bend, you have the internal arc, which is smaller, and the external arc, which is larger. And if you do the difference, this describes how much you are bending in that direction.
Okay.
So this is the physical interpretation. If you put the correct, let's say, quote unquote, the correct D.
Okay, got it. Thank you. Thank you. Appreciate it.
Great. So I see we're approaching the hour, but I hope you can stay with us for a few more minutes, Cosimo.
Of course.
I know I've got a few questions. So, and if anyone else has a question as I'm going, do raise your hand. So towards the beginning of the talk, you sort of motivated things by pointing out, you know, in nature, we've got this distributed, compliant mechanical behavior that really amounts to embodied intelligence. But then the control schemes you're describing all seem to rely on a centralized compute facility. So you're going to have some computer that brings all this information in, does some thinking, and then sends out the commands. So I wonder if you're aware of any work where people are working on distributing the computing as well as the mechanics. So I'm imagining putting many small compute sites distributed throughout the mechanical setup so that you don't have one larger computer acting as a deterrent to the whole soft robotics idea. Does that make sense?
That makes very much sense. We are going, and there are a lot of I think a lot of point of discussion to start here. This just came to my mind. I want to do just a little more of self-advertisement. We're going to have a debate sponsored by the Technical Committee on Soft Robotics, which it's will also be on this very topic, and the debate is going to be Monday. So if some of you it's interested, there are people that are. I will participate as a speaker, but there are people that are more, let's say, expert maybe than me on the topic. But yeah,
open to the public to attend.
Yeah, it's open to the public. It's sponsored. I can share.
Yeah.
Let me see.
After the
maybe
talk, I'll follow up with you and I'll get the link and distribute.
Okay. Yeah. That's probably the best way. Yeah. So let me give you at least two answers to these questions. The first one is more on a conceptual level, theoretical, and I think that softness here is really working as a controller. And although and if you write down the equation, you can really see that softness is having the behavior of an algebraic closed loop here. So another direction of research that I'm taking and over the year that I didn't have time to discuss here is to model and to shape the potential field as if it was a controller using techniques of control theory. In this way, you are directly embedding at least part of the control into the robot, the robot body.
I was hoping you were going to go there with your comment that it makes so much sense. Just to embed, if you can embed the intelligence, design it, right?
Yes, exactly. I still believe that a little of brain in the classic sense, so in stuff that is implemented using computation, will still be needed, at least for give some autonomy to the system. But I really believe that a lot of the stuff that I'm now putting in this explicit calculation can be moved directly to the body of the robot, to the elastic element. There is also a more technological answer to your question, which is about instead the research very interesting research that other people are doing, which is about soft. We could call it soft microprocessors, soft computers. So there are mainly efforts at Harvard in the Whitehead's group, and in Bristol, Rossitron recently did very interesting work on it, and in Edinburgh as well. A lot of groups are starting to repropose some old ideas about using no more electronics but fluidics to implement logic structure, logic components, logic ports, and I mean, in the end, you end up with quite big. I mean, they are able to build transistors using fluids, but in the end, you end up with a transistor which is, I think, as big, maybe bigger. Sure. So it's or a logic port or whatever logic system, which is quite big. But still, so you cannot really expect from these calculators to do the same kind of calculations that we have with the ones done in electronics, because I don't think there is really the hope to be able to make them very small. But
it seems, Cosimo, like there's this assumption in that work. Can you hear me okay?
Mm-hmm. Yeah.
There's this assumption that everything has to be made of soft materials to be a soft robot, but isn't very fine granularity good enough in some applications? So if the microcontroller was a speck of sand sized and embedded in a soft gel, wouldn't that be preferable to being limited to two logic gates?
I completely agree. I don't know about everyone directly tackling this problem. I mean, I actually doing something in that direction right now. I just submitted a paper to International Symposium of Experimental Robotics about it, and it's about, but it's for sensing. So to use small rigid sensors on the robot instead of distributed soft ones. And I think that I'm very much convinced about this thing, that you can you don't really need to do everything super soft. You can accept to introduce some rigidity within the robot, although it's a level of granularity that does not disturb the final softness, the main characteristic that you really want to reproduce of your robots. And in the end, I think that this picture here shows the two extremes of soft robotics that we have now. The one that is discussed today, which is the continuum one. So here we want to be as soft as possible, no matter what. And then we have these articulated soft robots that are a more established field, and there we clearly accept to have a rigid body, but still we can get a lot of the good property of softness and elasticity by just introducing springs in the correct position, or component elements in the correct position. And I think this is really another extreme example of how granularity plays. And I see as a future direction for the two community to, in general, the soft robotic community, to more and more get sense of this degree of granularity, and to not be extreme, at least for the continuum soft robotic community, in saying everything has to be soft because we are soft robots and everything should be soft. But there are gray areas.
Yeah, that makes sense. Cool. Thanks for that. I see that Guidong has been waiting patiently with a question, so please do fire away, Guidong.
Hey, Cosimo, thank you very much for giving us a wonderful presentation all the way from Europe. So actually, Don already asked the question I wanted to ask, but I want to comment that your idea and your suggestion of using environment as a control input so that we can realize soft motions is an excellent idea, which has been used in the area of quantum control. Delft actually has a powerful team in quantum control research. And one idea of traditional quantum control is that you shoot high frequency lasers to, for example, an atom, right? And therefore you will be able to regulate the behavior of this atom so that you achieve control goals, right? I think this is very much aligning with what you talk about here. And but I also want to ask, I think, the same question that Don asked from a technical point of view. If we were to continue this part of study where we try to use this kind of discretized controller to control a soft robotics with a continuum of dynamical states, what's the fundamental limitations? Will you be able to one day build an actual octopus using the framework you proposed here?
Yeah, so the limitations are many, and this is the reason why I am going more into the theoretical aspects that I briefly discussed before. I mean, this was just to give you a flavor on the directions, but I wanted to do that precisely because I really think this is a very important point, the one that you are rising. So what we have here is a description of the robot shape that it's still somehow discretized, but it's discretized in a functional space, and let's say it can be discretized in the functional space at a given level of precision. So you basically have this weights theta here that describe the state of your robot, and this is a continuum shape, and you can increase the number of theta and go as close as you want to the infinite dimension. And I think it's important here is that we are no more taking a segment and dividing it in space segment. We are just taking the segment, and as it is, we are instead discretizing in the space of function. So we are not undermining the continuum nature of the system by taking sub elements of it.
Okay.
That said, I still think that the method that I proposed before for this kind of robot is useful in the practice, because nowadays most of the soft robots are made in this way, as a discretized sequence of actuated segments, and this could be, as you said, limiting because we are not really having yet an octopus, a complete octopus. But still, I think it's a very important middle step from what we are to this final element goal, because you can really see you can really see each of these segments as if they were a continuum version of the classic joints of a robot. So I think it's really an intermediate step that it's worth to taking, but it's not the final goal. I agree.
Okay, thank you very much, Cosimo.
Thank you.
Good. Some more questions for our speaker. Maybe I'll ask one more from me. And so again, in your motivation, you pointed out, so far, at least, rigid robots are sort of dominating in practice. And I think a lot of people are excited and have a sense that soft robots are just on the verge of making headway into practical applications. I wonder if any specific applications are on your radar as being sort of the first, big thing for soft robotics to break into.
Yeah, so there are things in which soft robotics, I think, is already doing some very good job. and they are the ones related to, for example, assistive rehabilitation. So exoskeletons and soft exoskeleton, this kind of stuff. And I think the reason why this is the case, in my opinion, is because you don't really need a controller for a soft exoskeleton. I mean, you need it, but it's taking care more of the human part than the robot itself. So this in my view, it's a reason why this system works very well in this condition, because they don't still need any sophisticated controller to work. While in much of the other cases, they need it. At least this is my opinion. And another direction in which the soft robots, I think, are really another niche in which soft robots are really proving to be quite useful are soft hands. You can see three of them in. Actually, there is also a kind of a robot having a gripper here, so 4 of them, and really soft hands are I think are really revolutionizing the grasping field, because you can really grasp and manipulate objects in a quite reliable and way, and in a way that really resembles how humans think. I think, I mean, this is my opinion, the human thinks grasping, and not the classic way of having the precise control of all the interaction forces and movements. This is what we have now, and I think that these two fields are really very much already ready for the real world, and there are already companies producing soft hands and soft exoskeletons, so I'm very excited about that. If I have to say that the next big thing that we will have as practical real-world application for soft robotics is exploration. In one of the robots here, the one this one here is from Stanford, is a Vine robot, and the idea is that, and then there are also others coming around. And the idea is that you can have these soft robots either growing directly inside the place, or push it from outside. And since they are soft, they don't care if they go in contact with the environment, but actually they want to go in contact with the environment to use it as an extra actuation. So you can really reach for small places, entering in small holes, and so you can think of using it to do all the kind of very challenging inspection in narrow places, or rescue. I mean, of course, not bringing stuff or people outside, but you can think of putting a camera on the tip of the robot and going to see if, for example, there are people that are endangered in a disaster area or whatever. So I really see this as a next thing that can really go to the market, because I think it's quite close to be something that really works in the real world.
Great, exciting times for sure.
Yes.
Okay, very cool. So I see it's 15 minutes past the hour. Cosimo, you've been very generous with your time. I'd say, I'd love to keep chatting. Perhaps we should ask the audience for any final last-minute questions if they have any. Otherwise, I will invite everybody to thank our speaker. Feel free to type thank you in the chat window. I know it's not quite the same as a rousing set of applause. Abdallah's just posted a video of the Stanford robot. I think it's that, the yellow one at the bottom, I suspect. But otherwise, thank you very much, Cosimo, for the talk. And what I'll do is I will circulate to the audience the link for that event you mentioned that's coming up. It's a debate coming up on Monday, I think. So that's right.
Yes.
Okay, thank you very much.
Hope it will work with the times. Time window. It probably will be in the morning for you. It's 9 p.m. In Europe. So
it may, yeah. That sounds like it'll work out.
Okay, but I think it will be recorded as well. So if you're interested, so. Okay. Thank you very much for having me. It has been a very, very big pleasure.
Okay, it's our pleasure. Thank you, Cosimo.
Bye
Everybody
bye.
else, we'll see you again in a week at our regular time. Bye.